Is time travel possible? We hear about this kind of thing all the time in science fiction, right? It's interesting. I mean, we obviously perceive time on a regular basis every day. Yesterday was yesterday, today's today, tomorrow's tomorrow. We kind of all get time. We're scheduling, we have appointments, we do what we do. We largely think of our life within the context of time. But time travel is a different thing altogether. As far as we know, none of us are actually traveling through time. But we hear about it and read about it, see about it on in science fiction, right? We have our Star Treks, we got our Back to the Futures, H.G. Wells, all these kind of interesting stories. And I think it is always fascinating because we often like to think, what would happen if we could travel back in time? Would it be at the very least, I'm sure it would be interesting. Would it be a good thing to do? Maybe not. Maybe as per chaos theory, we would make those butterfly wings flap a little different and things would turn out well different. Maybe that's good. Maybe that's bad. Maybe that would be very, very bad. They get into these kind of grandfather paradoxes. What if you went back in time and killed your grandfather? Then you'd never be born. But if you were never born, then how did you actually travel back in time to do that in the first place? And all these kind of interesting things. It's an interesting topic. But for the most part, it just seems to be part of science fiction. But what if it wasn't? What if we could actually travel back in time or get something to travel back in time? Maybe not humans, but what if we could, pass information back in time? Or maybe small particles and things like this. Well, to get an answer to that question, I guess we'd have to ask science, right? We'd have to go to the theories of space and time and, essentially ask physics, is something like time travel even remotely possible? And if you want to get this question answered from physics, then you got to go to the main two pillars of physics, which is general relativity and quantum mechanics. Those are the two core leading theories. And they've been like that essentially for about 100 years now. And these are the theories that kind of are the ultimate bedrock or foundation of physics itself. And, they have aspects of them, particularly general relativity, that deal with time. So if you want to know if there's anything possible about time travel, that's where we have to go. So why don't we do that? We're going to do that in this episode and kind of take a look at the prospect of time travel scientifically, what science actually says about this. And then I'll fold that into some broader perspectives as I do going forward, what that means for science and even life in general. And hopefully you'll learn something in this episode about the prospect of time travel. So what we have to do first is go to general relativity. This is the main pillar of physics that deals with space and time. Most of you probably know that, but just a really quick kind of back to the basics recap. If you kind of want to know what gravity really is beyond, Newton's apple falling from the tree, you go to Einstein's general theory of relativity, which basically says that whatever mass you have in the universe, it tends to bend or warp this kind of unified notion of space-time. In other words, space and time are kind of woven together in this quote-unquote fabric. And if you have something massive like a sun or a planet, it's analogous to placing a bowling ball on a trampoline and having that trampoline be depressed down. It kind of warps the fabric. So the fabric of the trampoline is space and time, and the bowling ball would be something like the sun. And if you want to think about planets orbiting the sun, it would be like rolling a small marble on that trampoline, and you could see where that marble would go. It would follow in the language of general relativity, geodesic, but basically it follows the line that's easiest to follow as it goes through that warp space, and it just kind of keeps moving towards the planet, the bowling ball. In the case of planets, of course, they have their own, kind of velocity, so it balances out the going towards the sun with the constantly trying to move straight. Anyway, that's what we think of as gravity. It's a warping of the space-time. So what does that have to do with time travel? Well, because it's dealing with space and time, and more to the point, because it tells you how time tends to change as per that warping, then the question arises is, could you actually warp time enough to fold back in on itself? In other words, could you bend a timeline so extremely that it would go in the opposite direction, which would be something akin to time travel, I guess, right? So we think of time as being essentially an arrow of time. You have, think of it as going from left to right, yesterday, today, tomorrow, and it just kind of keeps going straight. We don't seem to have any control over that. But as per general relativity, if something could make the warping of space-time so extreme, then maybe the arrow of time actually folds back in on itself and goes back the other direction. Would that be a type of time travel, right? Now, again, we have to think about, well, what is traveling back in time? Like, is it information? Is it a particle that would be trapped in that warped space-time that's going backwards? We'll get to that in a bit, but this is why we would go to general relativity first and foremost to try to answer that question. And it's not enough to kind of just, ask general relativity face value. You kind of have to do a version of general relativity that would deal with an extreme version of the bending of space-time. So where can we get that? Well, general relativity has a number of different ways you can talk about it. We would call these like the solutions to general relativity. Kind of different ways of mathematically expressing what the theory can tell you. And one of those ways is called the Kerr metric. The Kerr metric. It's an exact solution to Einstein's equation. And as opposed to the kind of the run-of-the-mill bending of space-time, what it does is it says it tells you what space-time is doing in the presence of a rotating mass. So we could think of this as, imagine you had a black hole, which is presumably supermassive. And not only is it just kind of sitting there, it's actually spinning. And that spinning black hole would cause the fabric, quote unquote, of space-time to kind of get dragged around with it. I guess it's kind of like, maybe you're throwing something in the water that floats, but let's just imagine it was heavy, and you're also twisting it, and then you can kind of see the water around it twisting with the object, right? And this is called frame dragging, and just it relates to inertial, or it relates to frames of reference and different ways of thinking about what an observer would see, let's say as a particle or a person, if they did approached a super massive object like a black hole. But we'll put that aside for now. All that matters is that you can look at general relativity in such a way that it will tell you what happens to space and time when not only is there a mass there that's warping the fabric of space-time, but that mass is actually rotating. And that's interesting because that's what tends to lead to the kind of exotic or extreme twisting of space-time. In other words, it's like we're not just bending it, now we're twisting it, okay? Space-time is getting almost violently, if you will, dragged and along for the ride as, let's say this is a black hole that's rotating, okay? A black hole would be, massive enough to make this happen, and if it's spinning, then this frame dragging would be extreme enough to open the theoretical possibility of something like a CTC, which is a closed time-like curve. And this closed time-like curve is this idea of bending time back in on itself. It creates a loop. So just a step back, I said at the beginning, hey, time travel is interesting, but is it possible? Let's go to science. The first place to look would be physical theory like general relativity, because it talks about space and time, and we know that it changes it. It's mutable in that theory, right? And so the natural question would be, well, is it mutable enough that you could bend it back in on itself, that you could form a loop? And the answer seems to be yes, at least within the theoretical realm of possibility. There is an exact solution to Einstein's field equations called the Kerr metric, and it deals with not only mass, but a rotating mass, and that causes this kind of really exotic frame dragging to occur, which is like space and time getting twisted and turned to such an extent that in certain regions of the spinning mass, time might be able to actually cause a loop and fold back in on itself, called a CTC, a closed time-like curve. Okay, so we're in the realm of possibility. It's not completely out of the question, and there's other ways you could look at general relativity, right? There's interesting time paradoxes there. Someone leaves Earth and goes, approaches the speed of light, and to the observer, you'd get this kind of time dilation happening. Or if a person was on a spaceship and they were approaching a black hole, then to an observer, there would be some time dilation, right? Their clock would seem to slow down relative to us and all that kind of fun stuff. Time is just weird in relativity, right? Weird, at least to us, as we normally perceive it as humans. A lot of this is all just kind of thought experiments, right? Theory, mathematical equations that maybe that's a way to interpret it, right? Okay, so let's leave that for a second. That's general relativity. Now, the other one, as I mentioned in the beginning, is quantum mechanics. This is the other major theory in physics that deals with, well, everything, right? It's a core pillar of physics and therefore of science. And the reason why we got to go to quantum mechanics as well is that if you're going to ask science if something's possible, then ultimately both general relativity and quantum mechanics are going to have to say yes or no, right? They're going to have to somehow work together because they're both extremely highly validated theories within the paradigm of physics. Lots of evidence that general relativity is indeed the case. Lots of evidence that quantum mechanics is indeed the case. And so it wouldn't make sense for these two things to disagree with each other or for only one of them to give you an answer and not the other. Now, with quantum mechanics, this is a bit tricky, though, because quantum mechanics doesn't really deal with time or care about time. That's not really a good way to say it, but really what it says is quantum mechanics, time is immutable. Time is the way that you and I think about it on a daily basis. It just kind of ticks by like a clock. It's not something that warps or bends or twists or turns. It's not mutable, it's immutable. It just is, right? And quantum mechanics, the framework, the scientific theory, just kind of plays out against the backdrop of time as we normally think of time. So this is already a bit of a problem, right? If we want both general relativity and quantum mechanics to come together to give us an answer, but they already can't agree on this most basic thing, which is time. And this speaks to really the largest, biggest, outstanding problem in all of physics, arguably, is the inability to reconcile general relativity with quantum mechanics. These two core pillars of science have never been able to be successfully brought together, at least not to the point where there would be a general consensus or some obvious demonstration that they were working together. Theoretical physicists are working on this kind of thing all the time. That's why we have things like string theory, these different theories of quantum gravities and all this kind of fun stuff. It's because there's this big, almost embarrassing, outstanding problem in one of our major sciences, which is physics, which their two core pillars just don't seem to work together, like really, really not work together. And, general relativity is essentially dealing with kind of the big and the fast, and quantum mechanics is dealing with the very small. So they're very two different worlds, but still, they're both within our realm of reality. So you would think that they would kind of be following the same rules, and they just don't seem to, right? General relativity is classical and it's continuous and it's smooth, and quantum mechanics is small and discrete and probabilistic. General relativity is very kind of deterministic, the way we think things happen, in our everyday experience. But quantum mechanics is fundamentally probabilistic. There's not really kind of an exact identity to, let's say, an electron. It's kind of more of a smeared out probabilistic existence that exists as this thing that we invented called a wave function, and it gets very counterintuitive. Okay, so general relativity and quantum mechanics, just we've now never been able to bring them together successfully yet. That's arguably the biggest outstanding problem in all of physics. Is there a deeper reality there? And we'll touch on this in a bit. So we have a problem here, though, because we want to talk, we're trying to get an answer to this question of time travel. We can't just ask general relativity. Yeah, there seems to be something possible. In a way, maybe that's not even that surprising, right? Because, again, general relativity is bending time. So I guess as long as you could bend it enough, like a spinning black hole, because it's massive enough and it's spinning, then it's not that surprising that maybe something like that would be possible. And now we're not saying humans are traveling back in time. We don't really know what would be traveling back in time. But, again, just within the theoretical realm of possibility. But quantum mechanics, what question do we even ask quantum mechanics? Because it kind of just looks back at you and says, well, I don't care. I don't know. I don't bend time. Or quantum mechanics doesn't bend time, so I don't know how to answer that question. But there's been some stuff happening recently in science, particularly in experiments that deal with quantum mechanics, more specifically in quantum computing, that suggest maybe quantum mechanics does have an answer to this. And this is super, super interesting because, again, the biggest outstanding problem is to try to unify GR with QM, general relativity with quantum mechanics. And something you're going to have to do, all scientists seem to agree, is, at least one step in that direction to unification would be to get time to agree between the two theories. Okay, so let's talk about some of the stuff going on in quantum mechanics right now. From an experimental standpoint, which seems to be shedding light. Well, this kind of began with thought experiments in quantum mechanics. That's how Einstein started with his general relativity, right? He imagines something like a flashlight or a lantern, and he imagines what it would be like to try to catch up to the beam of light and all that kind of stuff. So in theoretical physics, it's good to really use your imagination, at least at the beginning, and do these kind of thought experiments to try to imagine what would happen and then try to formalize it later with mathematics, right? So people started thinking, okay, well, hold on, maybe there is a type of mutability, a changeability to time in quantum mechanics too. How might that happen? Well, the cool thing about quantum computers now, and if you want to know a little bit more about those, go check out my first episode in Science and Perspective, where I talked about those. They're pretty limited in terms of applicability to real-world challenges currently anyway. That might change. But what's cool about them now is you can kind of create true physical quantum systems and then study them, right? And they can get more elaborate than, let's just say, like the double slit experiment kind of stuff, where you're shining electrons through slits and you take a look at wave patterns and particle patterns and some kind of duality between them and all that kind of stuff. That's been around for a long time, obviously super fundamentally fascinating. But with quantum computing, you can start to take a bunch of different particles. You can entangle those particles physically, like not just abstractly or theoretically, like physically create real entangled systems, and then go try to measure them or try to understand something about them. And the two kind of main properties, I guess you would say, that are investigated typically within this type of situation would be quantum entanglement and quantum superposition, right? So quantum entanglement, again, you can go listen to my first episode, and many of you probably already know, but is basically this long-range correlation that happens between particles. So it's like if I took an electron here and then someone in the Andromeda galaxy had another electron, but those electrons were entangled. As soon as the person in the Andromeda galaxy went to make a measurement on that particle, the property of my electron particle would immediately be established. So there's this long-range, it seems like communication, but it's not supposed to be actual communication because, and again, this is GR and QM kind of arguing with each other, but, general relativity, as per Einstein, is saying nothing can travel faster than light, right? No information, nothing. And for there to be an instantaneous, quote unquote, communication between the two electrons in my galaxy and Andromeda galaxy, that would require faster than light travel. And according to GR, that's not possible. So it's really weird. And Einstein presumably called this, something like spooky action at a distance. And ever since, people are trying to debate what he meant by that. Doesn't matter. The point is, there's this really, really long-range correlation, and it seems to be completely agnostic to the distance between the particles. Doesn't matter how far apart you put them, they will instantaneously resolve themselves in the same instant. And you can show this experimentally. You can show this you can entangle two or more particles, and then you can go to measure one, which, if you're following kind of the Copenhagen interpretation of quantum mechanics, that would collapse the wave function. So that just means it all of a sudden takes on the property it's supposed to have. Another weird, counterintuitive, probabilistic thing in quantum mechanics is it's almost like things don't really exist until you go to measure them, right? Or they don't, at least they don't exist in the way that we measure them until you measure them, right? That something seems to kind of collapse in order for it to become what it becomes. Anyway, so that happens, and then if that was entangled to another particle, it immediately happens in the other particle. And the other thing happening in the other particle would maybe be like the opposite spin or some other property, but it's correlated and it's complementary, if that makes sense. Okay, so anyways, entanglement doesn't matter how far apart things are. As soon as you go to apart entangled particles are, as soon as you go to measure something, the other things happen instantaneously to the other particle. And you can actually use this, and you do use this in things like quantum computing. Again, you can go listen to my first episode, but this means that you can have these massively entangled systems, and then if you go to do something somewhere, it instantaneously happens somewhere else. And if this was in the realm of problem solving, you could kind of use this to maybe explore a lot of possibilities in parallel at the same time. You can kind of search through configuration spaces more rapidly. But anyway, let's not get into all that. Entanglement is this weird, crazy, spooky thing, and it definitely seems to be real. And then the other one is superposition, which basically says a particle can kind of be in all possible configurations at once until you go to measure it, at which point, which is kind of what I said before, then it collapses down into the one path or trajectory that it takes on, right? So it's kind of like I'm going to go measure this electron over here, and before I do the measurement, it's kind of all over the place. And when I say all over the place, it might literally be all over the universe. We don't really know. Maybe it's all over the room. I don't know. There's probably theories on what expanse that is. I don't think anybody really knows. It just seems to be like all possible trajectories within the realm of possibility that electron could take. It's doing that or something like that until you go to measure it. And then once you measure it, it collapses into the most likely configuration or the most likely trajectory. Then that's what you measure. Okay, so that's superposition. So entanglement, things are kind of seem to be correlated with each other no matter how far apart they are. And superposition is like these particles take on all possibilities or many possibilities until you go to measure them, and at which point they become the thing they become. Okay, so what does that do with time travel? Well, there's been some thought experiments recently that suggest there would be a way to set up entangled particles so that you could measure one particle that was of the entangled system, and then send something back in time, like a bit of information, in order to change how the other particle that it's entangled with was originally set up. So let's just step back a bit so you can understand why you would care about this. So there's an area called metrology, or quantum metrology, more specifically. Metrology is essentially just the science of measurement. So you're interested in how measurement works and how much information you can get out of things, which is obviously important because we're doing measurement all the time in science. So in quantum mechanics, if you have a quantum computing system and you're setting up this kind of physical quantum system to do your experimentation, a common thing would be to create your entangled system and then you go measure one of what you would call a qubit. A qubit is just going to be this fundamental quantum particle. It doesn't matter, like electron or an ion or something, it doesn't matter, right? A qubit is the particle we're dealing with, because that's what you do in quantum computing. So you entangle these qubits together. But when you go to measure one qubit, because it immediately kind of collapses the system and ruins everything, there's no way to know what you're going to get until you measure it. So you go to measure the qubit, you get some value. Just to make this simple, let's say it was like 30% information. It doesn't matter what that means. Just arbitrarily putting a number on it. So the information value or content or whatever it is you're after was like worth 30% to you. Okay. But then when you went to measure that, so you got the 30%, then you realize, well, I can tell from this measurement now that I've measured it that if I had prepared the other entangled particle a certain way, I could have got 100%. Okay, so in other words, I could have prepared this entangled system in such a way that I could maximize the amount of information I'm trying to get. Again, it doesn't matter what the information is, okay? But you don't know that until you do the measurement. There's no way to have prepared it optimally from the beginning because you didn't have that information. You don't get that information until you go to measure the particle. Then everything collapses, you get your value, you get your 30%, and then you say, oh, I could get that other 70%. I can get the 100% if I prepared that other particle this way. In other words, the only way to do this as good as possible would be to travel back in time or send information back in time so that you could prepare that other particle optimally. Okay? So it's quantum metrology. We're interested in measurement. You go to do a measurement. You only get so much information. You wish you could get all the information. But the only way to get all that information is if you could literally send something back in time to prepare the other particles that this particle you're measuring were entangled with in a particular way. So I hope that makes sense. So that seems like, okay, again, just not possible, right? Quantum mechanics doesn't treat time as mutable, so what else could we do? But some authors have shown, and I'll put some links in the description, that, initially through a thought experiment, and then there seems to be some experimental evidence that is maybe pointing to this being a possibility, that there is a way to send information back in time so that you could prepare the other particle or particles in this entangled system in a way that would give you that 100% information that you're after. Okay. And we're not going to go into a ton of details about how this thought experiment works. But the main thing that they're doing is something called post-selection. And so you can kind of think of it like this. When you have your entangled system, you also have a superposition. And that means like these particles are in all possible trajectories or paths that they could take. And some of those paths, you could argue, are actually consistent with backwards time travel. Okay. In other words, if you really want to just do the analogy here, you can imagine your qubit is it could do all these different things. And maybe one of those things it could do is actually loop back in on itself and travel back in time to a previous state. Okay. And that seems weird, seems odd, like why would this even happen? But just put that on hold for a second. The point is that out of all the realm of possibilities, maybe quantum particles could have something about them that are consistent with a CTC, a closed time-like curve. Now, normally we would never see this, right? Like we don't go do a measurement and see anything that suggests time travel has happened with these particles. But if you do post-selection, which is basically you keep the results you want and you toss out all the rest. So quantum mechanics, I mean, you could do this in any science, really, right? Science has kind of the file drawer problem and all this kind of stuff where you would choose the best results and then you don't really show people the bad results. It's not a lie, like it's real. You're just showing people the best results. Or a broader analogy might be something like social media, right? Like if you go and look at someone on social media, they're not necessarily lying to you, but they're going to be showing you the best themselves in the best light, right? They've kind of post-selected the results of their life and only showed you what was best. It's kind of like that. So you go to do a quantum mechanics experiment and you pick out the results that seem to be consistent with time travel. Okay, whatever that means. I mean, you can go read the paper. It doesn't matter. They would create a set of criteria that would say, okay, if this quantum mechanical particle was traveling in time, this is what we would see. Boop, boop, boop. And then you go to do a measurement enough times, and sometimes you actually see that. And then what you do is you throw away everything else that doesn't align to that criteria, and you just hold on to it. And so in one of the original papers, it was like 1 in 4 times you would see something happening when you went to measure the quantum particle that was consistent with time travel, and then you just threw the other 3 away. And then you just kept the good results, right? And they admit this. They're not like lying. They're just saying like we use post-selection, and it shows that there is a way that quantum particles seem to have some of their superposition and entanglement being consistent with time travel. Okay. So I hope that made sense. Now, okay, so now some people will say, and the kind of main term here would be retrocausality, right? This idea that essentially the effect is going to precede the cause, which is the opposite of what we would normally experience, right? And a lot of people would look at that and say, well, I don't know if this is really retrocausality happening in a quantum system, because you're post-selecting and you're kind of just picking out the results that favor the design of your experiment and tossing the rest out and this and that. But what I will say and what I will argue is that if it is true that you can post-select results that are consistent with CTCs, this closed time-like curves, in a quantum system, then presumably those loopy time trajectories were part of the superposition of the system, meaning something in quantum reality, even if you're almost never likely to see it, because, when you go to observe or measure things on a regular basis, you don't post-select them. But if they were in there, it means they're part of the makeup of quantum reality, right? Which is super interesting. If that's true, right? If this post-selection experimentation is actually possible and you can actually pick out these things that they really do align with a set of criteria that are consistent with CTCs, and that criteria is a good set of criteria and you're not missing anything, right? Assuming all that is good, then that would suggest that theoretically something in quantum systems are consistent with closed time-like curves. Okay, so let's just step back again. We said is time travel possible? We're going to go, it's interesting in science fiction, but let's go ask science. Specifically, we're dealing with time, so we're probably going to go to physics, and we got to go to general relativity. We got to go to quantum mechanics. General relativity, somewhat unsurprisingly, although still pretty cool, suggests that, yeah, it's probably theoretically possible because we're warping time all the time in general relativity. And if you could warp it enough, then why wouldn't time just fold back in on itself and create some kind of loop? Again, we don't really know what that means. Doesn't mean people are going to travel back in time, but presumably you could bend time enough to fold back in on itself. So yeah, GR says there's probably some kind of possibility to something akin to time travel, right? And again, time dilation and all this kind of stuff says that too, presumably. That's one way to interpret it. And then quantum mechanics, which up until recently has never really said much about anything to do with time travel, you could actually set up quantum computing systems, you can entangle particles, and you could take advantage of the fact that they're entangled and superpositioned, and you could pick out the results in such a way that they seem to be consistent with the possibility of closed time-like curves happening in quantum systems as well. Okay. Again, I'm not going to get into all the details, but hopefully that basic experimental setup with post-selection made sense. And so theoretically, now this would be exciting if this is all true, even just theoretically true, meaning like it really is consistent with the theories, because it would mean both general relativity and quantum mechanics are saying, okay, yeah, I think it's in the realm of possibility that something like time retrocausality, right? Time going in the other direction could occur as per these CTCs, these closed time-like curves. So that's exciting. That's exciting to try to get just an answer to time travel, even though we don't really know what that means yet. What is a closed time-like curve, right? But maybe even more exciting is maybe that's a potential unification path to general relativity and quantum mechanics, right? Because again, these are the two pillars that can never be brought together. And one of the reasons it can't be brought together is because they think of time so differently. They treat time so differently between the two frameworks. But now we've got this possibility that maybe there are closed time-like curves in both general relativity and quantum mechanics, meaning in some sense there might be a way to treat time the same between the two frameworks. Okay, And so that's kind of what is, and that's kind of what's happened in recent research. So let's kind of do some speculation now. Let's have fun with this. Let's go, and then I'll fold that into kind of my broader perspective and commentary on science in general. And I think that'll be interesting. So we got it in GR. We might have CTCs in quantum mechanics as well. So I would argue, as I think some others would, is that we would think these must ultimately be the same thing, right? It being the CTCs, the closed time-like curves in GR, they should be the same thing as the closed time-like curves in quantum mechanics. Well, is that true? Well, actually, a lot of people don't think that's true. At least that's not the way it's being presented currently. It seems to be that whatever closed time-like curve thing you're getting in quantum mechanics is maybe like analogous to the general relativity thing, or it seems to kind of, lead to the same type of results, but the physical system seems to be very different, right? Like in general relativity, you have this massive black hole that is spinning to give you the closed time-like curves. In quantum mechanics, there's nothing like that. You don't have, big masses. You don't have spinning masses. It's just this entanglement and this post-selection that's giving you closed time-like curves. So the physicality, the physical system that's giving, presumably, the CTC seems to be completely different. But I would argue that they must ultimately be the same thing, right? Because otherwise you're not really unifying anything. And if we're talking about the same reality, general relativity and quantum mechanics have to somehow be speaking to the same underlying reality. I mean, just logically, that would make sense. So what's going on here? How can we have, assuming the theories are correct, a spinning black hole giving the same thing as an entangled quantum system? Like they don't seem to have anything in common with each other, but they both speak to CTCs. So maybe that's a path to unification, because if you could answer that, how these two seemingly different things produce the same thing, a CTC, then maybe you'd find out that they're not actually that different at all, and that would help you unify the worlds of general relativity with quantum mechanics. So I hope that made sense. So what can we do about that? Well, let's think about, let's go back to, and this is a lot of speculation now, and this is kind of me having fun with the theory, but I think, stick with me because I think it'll be interesting and it'll teach you more about the concepts. Let's think about this just kind of informationally. Like what is happening similarly between the general relativistic system and the quantum mechanical system? Okay, so let's go back to general relativity. If we want to bring the two worlds together, GR and QM, then a good way to do that, arguably, is to take something like a black hole and have a small particle approach it, right? Because the big black hole, is from general relativity, because that's the type of things that GR deals with. And the small particle is from quantum mechanics, because that's the type of thing that quantum mechanics deals with. So what would happen if we take a small quantum particle, I don't know if it's a qubit or an electron, whatever, it doesn't matter, and it approaches, the boundary, you might say, of a black hole? What would happen? Well, we can go back to that Kerr metric. That's an exact solution to Einstein's general relativity. And you can look at that Kerr metric in such a way that it can kind of tell you what happens when a particle, or what you might call a test mass, approaches something like a black hole. What would happen? We know it would presumably get caught up in that frame dragging I was talking about, right? Again, you got the spinning black hole, space-time, the fabric is getting all twisted and turned. So presumably a particle in the fabric of space-time, which it would be, is getting twisted up. And you can even go on Wikipedia and see this. You can kind of see a GIF, kind of like an animation of this test mass approaching a black hole. And it starts to, as you might imagine, kind of go crazy. It starts to fill up a big volume of space with all its possible trajectories. Okay? Which is, I guess, kind of a fancy way of saying the particle gets close to the spinning black hole. It starts to experience the frame dragging. It starts to kind of get caught up in the eddies, if you will, of the fabric and space-time as the space-time gets twisted, and it just starts to kind of go wild, which is not really that surprising, I guess. Now, we don't really know what this means. Like, what do you mean go wild? Like, is it the same one trajectory that's just flipping and flopping all over the place? Or does it start to kind of take on different trajectories the way you would see in superposition? Let's not get into that. Just think of the particle as starting to take on a lot of different possibilities because it's getting caught up in the twisting of the fabric of space-time close to the black hole. Now, what's interesting about that is this actually ties us to the notion of information. Okay, which is a good thing, because if you can focus on the information of what's happening, you can separate yourself from the underlying physicality of the systems, which we need to do here. Because we said the closed timeline curves in quantum mechanics are coming from something physically that seems completely different than the closed timeline curves that are coming from general relativity, right? Quantum mechanics, they're arising from post-selection and little qubits that are entangled and superposed in superposition. And then general relativity is coming from a spinning black hole. So the physicality is very different. We need to be agnostic to that. We need to separate ourselves from the underlying physicality and just focus on the information. So how might you do that? Well, when a particle starts to go crazy, okay, and this doesn't have to be a black hole. This is just true all the time. When it takes on a lot of different possibilities, you're actually, in some sense, increasing the information content of the system. That sounds a bit weird. Why would you be increasing the information content? Well, the way that we tend to define information in an information theoretic fashion is related to entropy. Basically, it just means that the more kind of messed up or disordered something is, the less you know about it. And the less you know about it, it means there's more things to figure out, right? There's more what you might call surprisal in the system. So if we have this particle approaching a black hole, before it gets to the black hole, there's a lot known about it, arguably, right? It's this particle and it's traveling in this direction, let's say. But as it gets close to the black hole and it starts to undergo frame dragging and it's getting twisted and turned, there's a lot more uncertainty, obviously, right? No different than, if you had something floating in the water and then another thing approaching it, and then you made the water very turbid and wavy, it'd be very hard to know what that little particle around the big particle is doing. And it's no different, right? It's just the particle approaches the black hole, starts whipping around, and scientifically we would say it ergotically fills the space or kind of a toroidal region around the black hole. But don't get caught up in the jargon. It doesn't matter. It starts going crazy. There's more uncertainty now in what that particle's doing, and you can think of that as there's now more information content. There's more things to learn about that particle because we don't know now where it's going. You'd have to work to try to resolve that information. So we could say that as the particle approaches the black hole, the information content is going up. Now, this is kind of interesting because what do we know about information? Well, information is computed. In fact, we can really think of all of nature as being one big computer, for lack of a better word, because it's processing information all the time. Obviously, we have this conversion of matter and energy into new things on a regular basis, right? The sun's energy is coming in. We're getting these transformations, these chemical reactions. There's always an input and there's always an output and there's a transformation in between. And that's really what a computation is, right? We think of computing in terms of, information that we're typing on a keyboard, and then transistors are kind of this black box in between and does some transformation, and then we get an output on the screen, but that it doesn't matter. Computing is inputs being converted to outputs, and nature is doing this all the time. So it's totally legitimate to think of nature as computing, and what you do computing on is information. Okay. So now we got a lot of things going on. So let's step back and get the full picture here, and I'll try to impress upon you why this seems to be important and might be a kind of way of thinking about how to unify these worlds of quantum mechanics and general relativity, and maybe answer our time with respect to time travel. Okay, we said general relativity, black holes, spinning, bending time. Okay, it makes sense. Quantum mechanics recently says, look, you can do that too, but we're not talking about spinning masses and stuff like that. You can entangle particles and they can have really crazy trajectories, and some of those trajectories might actually be consistent with time travel because they get really loopy. And so we post-select the loopy ones and we go, oh, look, maybe you can have closed timeline curves in quantum mechanics as well. Cool. Now we got general relativity and quantum mechanics saying the same thing can be produced, theoretically. But they're being produced in a completely different way. The physical systems seem to have nothing to do with each other, right? Spinning black holes versus quantum entangled particles, completely different. So that's not going to help us unify or answer our questions. So we need to kind of be agnostic to the underlying physicality. A good way to do that is with respect to information. So how can we get at the informational aspect of a system that forces QM and GR to work together? Well, why don't we take a spinning black hole? Obviously, this is a thought experiment. Take a quantum particle and smash them together. Have that quantum particle approach the black hole. Now, at least theoretically, you're forcing yourself to consider the reconciliation between general relativity and quantum mechanics. And what do we know about that particle? Well, you can look at the exact solution to Einstein field equation, one of them known as the Kerr metric, and it says that particle goes crazy. Particles that go crazy tend to increase the information content of systems because there's more uncertainty and there's more to figure out. And if it is increasing the information content, that means that if you think about nature as computing, as a big computer, that information must be getting computed. It must be something that's getting transformed by nature to produce its outputs. Okay, so let's jump into computation so we can put this into context here. So when we think of computation, one of the main ways to think about it is in terms of the space-time trade-off. And this is not the same space-time as we talk about in general relativity. This is related to space complexity and time complexity. It has to do with how well, or really how fast, an algorithm can solve a problem. That's what we do in computing, right? You make algorithms, which are basically just sets of steps that get followed until a result is achieved at. So you want those things to go relatively fast. You don't want to wait around forever. And so you have the space complexity of that algorithm, which is how much memory is going to be required for that algorithm to do what it does. Then you have the time complexity, which is how much time it's going to take to actually solve the problem. And so you kind of want both to be low, right? Like you don't want to use a ton of memory because that's expensive, and you don't want to wait forever because that wouldn't be practical. And so there's the space and the time complexity considerations when you go to create or design algorithms, right? And it's typically a trade-off. It is a trade-off, right? So if I throw more memory at the problem, I can speed a slow algorithm up, but again, there's the cost of more memory. Or I could try to make my algorithm more efficient more quickly, and then it would use less memory. But now you got to put all that effort into trying to get the time complexity down, and it might not even be possible. So there's kind of this trade-off between memory and time. And anyways, it's just something that goes into the consideration of designing algorithms. But this is specifically for deterministic algorithms that if you put the same input, you're always going to get the same output, right? It's an exact set of steps. It works exactly the same every time. It could break, it could have a bug in it, but that's just part of something getting in the way of the determinism, right? It doesn't change the nature of the algorithm itself. Okay, so why are we talking about this? Well, nature doesn't really compute like that. I said, we can think of nature as a big computer. It converts inputs to outputs. That part is the same, but it's nothing about it smacks of deterministic algorithms, like some exact set of steps being followed. Some might argue, well, maybe it still is deterministic, but it's just so complicated we can't see the determinism. We can't peel back the layers and see what part bumps into what part. And I would argue it's not that, actually. It just is fundamentally non-deterministic. So you don't get the same output for the same input because the actual nature of computation, the way nature computes, is fundamentally different than the kind of simplistic rules-based algorithms that we come up with most of our software. In fact, nature is more akin to what we're doing with deep learning, which would be much more non-deterministic and probabilistic than what you would see in, the rules-based kind of software that we get if AI is not involved. Anyway, I would argue that nature is definitely, being non-deterministic. And so what does that mean for what we're talking about in computation? Well, let's go back to that time dilation idea. And I promise this will all kind of come back to our, unification of GM and QR in a second. But let's think about time dilation and general relativity. Again, if you're looking at someone as an observer, you're watching someone approach a black hole, you're going to see their clock tick by slower. Okay, that's essentially time dilation. It's one of these funny things that happens in general relativity or due to general relativity. Or due to physics, but to which general relativity expresses, right? Okay, so we have time dilation occurring. Now, this could just be, that's just reality, right? Like there's just this funny thing about, your frame of reference versus mine and our relative velocities with respect to each other. And it kind of makes everything just relative. But if we think about this computationally, maybe what time dilation is let's say it's the large mass, which is a black hole. Well, maybe that large mass is squeezing the amount of available space available for computing. So again, I'm saying all of nature is a computer. It's computing all the time. So the black hole is in some sense involved in a computation, whatever that is, right? There are inputs and there are outputs. I guess in the case of a black hole, sometimes you don't get the outputs because the information is lost forever, although we don't really know that for sure. But anyways, there's a computation happening. Things are getting transformed all the time. So maybe that black hole is squeezing the amount of available memory that can be used in the computation. Well, that would mean that the time complexity would essentially explode, right? Things would take a lot longer to happen. And maybe that's what time dilation is. You're looking at somebody approach this large mass. That large mass is squeezing the amount of space that's available. And because of the space-time trade-off, the space complexity-time complexity trade-off in computation, that forces the amount of time an algorithm has to compute to take a very long time. And so that would kind of be like seeing someone start to slow down as they approach the mass. Okay. Now, I'm not saying physicists think this is what's happening. I'm not saying it, there's probably some theories that are kind of related to this, but let's just speculate about this as we think about how computing might relate to the theories of general relativity and eventually quantum mechanics. So I said the space-time trade-off in computing is something that is, it only makes sense when you view things deterministically. Like it relates to deterministic algorithms, the deterministic lens. And that is how typically people, humans, we think about things deterministically, right? Our brain doesn't compute deterministically, I would argue for sure, no, but the way that we view things in life, we think of them kind of as a recipe, almost like an algorithm. If I ask you how you do your job, you'll say, well, I do this, and then I do this, and then I do this. Like, that's how my day went. In reality, it was probably a lot more nonlinear and a lot more non-deterministic and messy, but we make sense of our world by viewing things through the deterministic lens, as though they have a specific order to them, right? And this bumps into this, which bumps into this and bumps into this. Everything has kind of a cause, right? That's the way we make sense of the world. May or may not be true, but that's how we make sense of the world. That's how we organize knowledge in our minds. So as humans, we are viewing things through the deterministic lens. Maybe that's what time dilation is, though. Because we view things deterministically, that means that we can't help but see someone close to a very large spinning mass as undergoing time dilation, because under the, through the deterministic lens, the amount of space would be squeezed, and that would explode the time complexity of whatever processing has to take place. So people would be moving slower in that regime. I hope that makes sense. This is all very abstract, and again, how much of this is perception versus the actual physical reality, that's up for debate. But if you were to look at things through the computational lens, that might be one way to do it. So maybe time dilation is nothing but an artifact of our perception, not an actual computing reality. And I say that because nature does not compute deterministically. Not many things would point to that being the case. That's still debatable. Some people might say, well, I think whatever computation nature is doing, it is still deterministic. It's just so complicated we can't see the determinism. Maybe, but I would argue that, things definitely point, if you look at, complex systems and you look at the fact that virtually everything emerges, right? It's much more to do with emergence and information and feedback loops, and the large scale things take on properties that are not found in the pieces of which those systems are comprised, and on and on. It's very much about non-deterministic type computation. So that would mean things like time dilation is more just an artifact of our perception, because we tend to view things through the deterministic lens. It's not an actual computing reality. The computing reality would be much more related to non-deterministic calculations. And in non-determinism, the same input is not giving you the same output. It's not an exact, this bumps into this, bumps into this, bumps into into this recipe. Things happen in parallel. Things are non-linear. Things fold back in on themselves. The possibility space is explored kind of all at once, or all, it's a messy trial and error kind of system. And then the answer pops out of that. That's kind of a way of thinking of non-determinism, right? And that's very much what, if you look at the theory of evolution, if you look at natural selection, if you look at really any process in nature, it doesn't fit into, unless it's an extremely simple system, which is not what you see in nature. You see complex systems. When you look at nature systems, they do things very much non-deterministically and emergently. Okay, so I would argue that in order for nature to compute what's needed, it must do so non-deterministically. It has to explore all or many paths, and therefore, let's go back now to that particle approaching the black hole. Perhaps the particle whipping around near the boundary of a black hole is in fact the non-deterministic computation being done by nature to compute what is needed. It is how nature approaches its upper bound on information. In other words, determinism would never be able to compute what's needed, because under determinism, time dilation brings computing to a halt. So there's something wrong with looking at things deterministically. Maybe when time dilation occurs in general relativity and the clocks slow down, the reason why that's so weird and counterintuitive is because it's a limitation of our perception, not what's actually happening, right? So this would mean that some of the particles around a black hole would travel back in time in order to establish a computational bridge that preserves the information processing the universe must do. Okay, so let's just step back a little bit in case you're getting a little bit confused. We said we want to bring quantum mechanics and general relativity together. One way to do that is to put a particle, quantum particle, and have it approach a spinning black hole. Now you got the two worlds right now, GM and GR or QM and GR, are kind of being forced to reconcile, if you can do it. And so you've got this particle, and so what you do is you look at the Kerr metric, which is an exact solution to Einstein's general relativity, and that tells you what happens when you have a large mass that's spinning, and it can tell you what happens when a little test mass or a particle approaches it, and it says that particle kind of goes crazy. And we said that, well, but now there's more disorder, there's more uncertainty, and that's actually higher information content. If that's higher information content, now the universe as a computer needs to compute that, because that's what you do with information is you compute it, right? Whether you're nature or otherwise. That's what happens to information. Either it just sits there and does nothing, or it gets computed. We know that nature computes it. We know it has transformations. It's got chemical reactions. It's got all this phenomena. It's really what phenomena are, is the transformation of information into new things all the time. So now that information that is kind of exploding from that going crazy particle around the black hole as the information content, it's almost like a pressure that's rising, and nature has to do something with it, so it has to compute it. And what I'm saying is that we can think of that going crazy particle as kind of the non-deterministic computing that now needs to happen, okay? And so nature starts to, in some sense, compute that. And so so that would mean that some of the particles around the black hole, we said that we already know from the curve metric that there's a theoretical possibility of closed time-like curves, right? So out of that crazy particle mass, some of those paths or trajectories of the particle might be whipping back in time, right? As we said earlier in this episode, right? As I said, there's closed time-like curve possibilities. So maybe what those closed time-like curves are is a way to establish a computational bridge that preserves the information processing that the universe has to do. In other words, you need more paths. You need more trajectories. There's not enough trajectories to compute what's needed if everything happens in this nice deterministic computational regime. It has to go crazy. The particle has to go so crazy and so exotic that it might even have to travel back in time. In other words, the existence of closed time-like curves in your particle is like more paths. It's more paths that could be explored. It's more information that could be made available because the amount of disorder that you could add to the system. You need your particle to go more crazy. And the way you make that particle go more crazy is to have more paths than are available in kind of the run-of-the-mill situation where you don't have time travel. But time travel introduces more paths because you got them looping back now. Okay, so perhaps so now think about this. Perhaps what we perceive as mass is really just heavier computation arising from higher information content from more intense entanglement. So now I'm going to bring entanglement back into this, okay? And so what I'm saying is that maybe entanglement is everything. Like maybe general relativity and quantum mechanics both come together under entanglement. And again, the weird thing was like, well, if you have an entangled system, where is the mass? Where is the spinning black hole? But what I'm saying is maybe mass itself is a kind of perception. Maybe what we're perceiving as mass is just heavier computation arising from higher information content, which comes from more intense entanglement. So this would mean, to bring it all together, that entanglement, those long-range correlations that are, let's say, everywhere in the universe as a fundamental aspect of our reality, causes an increase in information content, which means there's more to compute, which means there's more whipping around behavior of particles to form CTCs, which provide more paths to explore in the configuration space to solve the problem, which is what nature's doing when it computes. It's always solving a problem, which leads to patterns, structure, and mass. So this is kind of the reverse of how we normally think of information. We think of the presence of structure as changing the informational landscape that gets computed, but perhaps mass is actually just a perception based off computation. Maybe it goes the other way around. Maybe it starts with entanglement. The entanglement in whatever original virtual or real particles exist in the universe, that entanglement raises the information content. That information has to go somewhere, so it has to get computed. And the way it gets computed is by having a bunch of trajectories go all over the place, because that's what it's like a non-deterministic calculation where many possibilities are being sampled. And because you need so many of those possibilities, you need to include CTCs, closed time-like curves, to have enough possible trajectories to be sampled in the computation. And then eventually what you look at in general relativity when you're looking at the curve metric is not, oh, the mass is already there and the mass is spinning and then here's what happens. It actually started with quantum entanglement. That increased the information content and led to something that we now call mass. Okay. So that might sound really crazy. It might have been a little bit hard to follow, but it's fun to kind of speculate a little bit, and hopefully you're kind of follow that a little bit. So let's just kind of really do a quick recap to bring it all together. We said at the beginning, is time travel possible? In order to answer that, you'd have to ask, physics, and you'd have to go to the main two pillars, which is general relativity and quantum mechanics. these things, these frameworks, these theories don't work very well together. They treat time very differently. That's one of the main reasons they don't work together. General relativity tells us, yes, something like time travel or closed time-like curves is maybe possible if the mass was big enough and it was spinning, and you can look at the exact solution to Einstein's field equations, one of them called the Kerr metric, which will show something like closed time-like curves is maybe possible. Quantum mechanics until recently didn't really have anything to say about this, because time in quantum mechanics has always been immutable. But if you look at some of these interesting thought experiments related to post-selection, it suggests that maybe there is, something in the entangled and superpositioned system of a quantum system. Something in there could be consistent with closed time-like curves. Okay, and you can post-select those results out potentially, and therefore CTCs might be possible in the quantum realm as well. So now we have a path towards unifying quantum mechanics and general relativity, potentially by looking at these closed time-like curves, and these are kind of treated as different things, though, right? We say, well, quantum mechanical CTCs are coming from entanglement, and the ones in general relativity are coming from spinning masses, and these don't seem to have anything to do with each other. But I'm saying and arguing that if you really want to bring these two theories together, they must ultimately stem from the same physical reality. And so we forced quantum mechanics and general relativity together by saying, let's take a quantum particle and have it approach the boundary of a black hole, or, somewhere maybe within the boundary or slightly outside the boundary. It doesn't really matter for the sake of this conversation, wherever that most exotic behavior is going to happen to that particle. And you can look at general relativity and it says, here's what that particle is going to do. It's going to go crazy. It's going to take a lot of different trajectories. And then I said, well, we can look at that information theoretically, because anything that takes a lot of different trajectories is actually increasing the information content. And now we can say something is similar between general relativity and quantum mechanics. And when we bring the particle to the black hole and we bring these two worlds together, which is the information content is increasing. And if the information content is increasing, then presumably that needs to be computed, at least if you're willing to look at the universe as essentially a computer that has, which I would say is totally legitimate, because you have transformations from inputs to outputs. So now you have this universe that needs to compute this accumulating information that occurs, which I said likely through entanglement, right? Because entanglement also increases the information content of a system, right? If you have all these long-range correlations, you have more possibilities in some senses. You have more uncertainty is another way to think about it. So the information content increases through entanglement. That information content needs to be processed, so it gets processed by the universe. But you need a lot of different paths and trajectories to do the computation, and so you need to tap into CTCs. You need more trajectories than just a regular non-time traveling particle would give you. And so the CTCs give you a lot more possible paths, and now you have this non-deterministic computation. And on and on and on, and eventually get to the point where we say, okay, so maybe what mass is. Now, this might still be consistent with mass being an excitation in the Higgs field. We don't know. Maybe it's still, I don't know if this is necessarily different than that, right? Maybe it's just another way of looking at it. But maybe mass is actually kind of a perception, because what you're perceiving is heavier computation. And so it all kind of stems from entanglement. And so really, and you could say, the whole kind of argument here is that everything is essentially emerging, right? Mass is emergent, pattern and structure is emergent, even the information is essentially emergent, because fields can emerge. It doesn't just have to be particles. Maybe all phenomena at its most basic level is an emergent phenomenon, and it begins really with entanglement. And once you get entanglement, you get the information. Once you get the information, you get the computation. And once you get the computation, you get what we perceive, whether that's mass, pattern, structure, or because we tend to look at things through the deterministic lens, it could be time dilation itself, and you start to see things slow down. Okay, so a lot of speculation there, quite a bit of jargon. Hopefully I didn't lose you too much, but the main take-home message here was to rise above quantum mechanics and general relativity and find a way to think about them agnostically, and I think thinking about them in the context of information and computation is a potential way to do that. Okay. So I'm just going to fold this now into kind of the broader kind of, what's the take-home message here? What's the broader perspective here? Well, from a complexity perspective, look, information really is how things work. I think I'm not saying my speculation is particularly correct, but I think the direction of looking at things informationally is, because information is ultimately how things work, right? Nature follows universal laws that apply across vastly different systems. And that indicates that structure and behavior of phenomena are governed by informational rules rather than unique physical attributes. So rather than just look at general relativity and say, well, this is specifically a spinning mass, and so that's where the CTCs come from. Or you go over to quantum mechanics and say, well, you have entanglement and you have superposition and you can post-select, so that's the physical system where CTCs come in. As long as you focus on the physical details of the systems, you're not going to be able to bridge quantum mechanics and general relativity. And that shouldn't be surprising because it is information that is agnostic, right, to the underlying physicality. Still depends on the underlying physicality, but it is ultimately agnostic, right? I can have a marshmallow and a piece of metal that are both 40 degrees Celsius temperature, right? Those marshmallow, the marshmallow and the piece of metal don't have much to do with each other. They're physically very different systems, but informationally they have the same thing. When you look at information, you find what tends to be related across things that superficially might seem different, okay? And, obviously physicists don't think they're looking at general relativity and quantum mechanics in a superficial fashion, but sometimes if you're not focusing on the information and you're just too tied to the underlying physical reality that you assume is there, that can actually happen. So nature follows universal laws that are much more informational than they are physical. Another point is I can look at biological processes, right? We know they rely heavily on encoded information like DNA, right? Deoxyribonucleic acid. They shape the organisms rather than specific atoms making up the molecules, right? It's more of an informational thing than a physical thing. Again, I'm not saying the physical part isn't there. Obviously it is, but it's being dictated by the information. Back to quantum mechanics, the particles that we describe in quantum mechanicals are really described by probabilities, right? And what you might consider informational states rather than specific positions and momenta. And it's very much a statistical way of looking at something. If you think about the behavior of particles, it follows informational probabilities, right? That's what dictates the interactions. And really, again, this just suggests that information, in this case in the form of quantum states, is what's governing the nature of particles. It transcends the physical makeup. And just complex systems in general, I alluded to this a few minutes ago, they exhibit emergent behaviors. It depends on interactions and information flow rather than the unique physical components of the system. You can have different systems arrive at the same thing. You can have like convergent evolution, for example, very different physical things, and then all of a sudden they start to physically become the same thing. It's an informational phenomenon that's taking place. So information is really how things work, and I think that's how systems should be looked at in science or otherwise. And I'd argue that our current paradigm is too reductionist, too focused on specific causes, that it really tries to force one framework into another. In the context of trying to unify quantum mechanics and general relativity, we get theories like quantum loop gravity, which is kind of trying to quantize gravity. And maybe that's the approach, but why should you have to quantize gravity, right? How do you know you're not supposed to make the quantum realm more continuous? How do you know it's supposed to be one into the other at all, right? Why wouldn't it be something deeper? Why are you trying to force one framework into another? It seems like a non-starter. Quantum mechanics describes small scales where particles and fields have discrete probabilistic behavior, as we talked about, right? But then in general relativity, space-time is a continuous curved entity and it's shaped by mass and energy. It's just such a different thing physically. And the attempts to reduce gravity to a quantum force via hypothetical particles like gravitons, that's going to always face issues because gravity's effects are inherently geometric and continuous. They're not discrete from what we can tell. And trying to make it discrete, or vice versa is a bit goofy, really. It seems like we're missing something deeper, right? There's a good chance that space-time and gravity are actually emergent phenomena, as I mentioned recently, right? Just a few minutes ago. It is a good chance that it arises from more complex interactions within a deeper structure of our reality. So if you try to reduce space-time and gravity to basic particles or forces, that might be misguided because these properties emerge only at specific scales. And just look, reductionism in general, it often seeks deterministic laws, but quantum mechanics ain't deterministic, right? It's a very much inherently, fundamentally probabilistic. Whereas general relativity does seem to be maybe a little bit more deterministic, and I dealt with a little bit of this. If you step back and think of things informationally and therefore computationally, you start to view things like time dilation or other things in a slightly different lens. I don't know if that's right, but I think it hints at a way of looking at things differently, and I think that's important. So what's the broader perspective here? I think it's important to think about what this type of science, looking at, how can we look at the world through this scientific lens, right? What's the broader perspective for our lives, for our decisions that we make? Because I think there's always something to learn. And our theories and life decisions go better when we focus less on specifics and more on informational patterns that the things share. Okay, so like some real life examples, imagine instead of obsessing over the exact number of calories in every meal, or the precise duration of each workout, you could take a more general informational approach and say, like, I'm just going to aim to eat mostly whole foods and stay active. Now, the latter is much more general, right? It's not very specific, it's not detailed, and yet it's likely to be more successful. Because counting calories is a very specific thing, and it comes baked with a lot of assumptions about really, the physical way that, the body might lose weight if that's what you're after, right? And we don't really know that, right? We don't have that deterministic aspect. And I would argue it's not even happening deterministically at all. But if you take a higher level informational target and say, eat just whole foods and stay active, even though it sounds way more general, and it is, it's more abstract, a lot of things subsume into that higher level of abstraction, and you end up being more successful. Another example, you're learning things, right? If you want to learn something new and get a strong grasp of it, often the general concepts will allow you to apply them flexibly across new situations. But if you focus on specifics, it can actually limit adaptability. Our current paradigm kind of tells you, devil's in the details. You got to learn the details. You got to learn the specifics. But that's actually a very fragile way to learn. It makes much more sense to rise above the details and see how certain things stick when many other things change. And that kind of invariance in the general sense is actually a far more effective and more adaptable and stronger way to learn. And even a deeper way to learn. The details don't mean deep, because details kind of come and go. They're always in flux, and they're kind of ephemeral, quite frankly. So that's not deep, right? Deep is what stays, and what stays is the higher level abstract patterns and things. Obsessing over minor budgeting specifics might be another example, right? You could try to budget everything and then end up broke because all of a sudden something happens in a month that wipes out all your savings because there's larger patterns at play, right? Focusing on high-level goals and outcomes can actually lead to better productivity than getting lost in the weeds. And there's all kinds of examples like this. So it's no different. It doesn't matter if you're doing theoretical physics, if you're doing something else. At the end of the day, you need to be able to think of things in kind of a physically agnostic way. Think about things on informational terms, higher level, more abstract terms. They tend to be far more powerful ways of learning and understanding what is actually happening. And I think that's hard for today's physicists to, quite frankly, get their head around, although some of them head in that direction because they're in physics, right? They're thinking about the physical reality of things. They want to pin it on what is actually happening physically, but that can be quite limiting. And I think maybe the better way to get there is to think about things informationally, right? So, just going forward, how can we approach the world through this episode's scientific lens? Well, just think about what are the theories that you hold about the world. Are you focusing on their specific embodiments, or are you thinking about their more general attributes? I would argue that you should focus on the latter. What do your theories, views, and opinions have in common with other views, right? What are those analogical connections between them? They seem superficially very different, but maybe there's a deeper informational structure that they have in common. Think about your life, think about the decisions you make, and if you start to approach things kind of more physically agnostic and more informational terms, I think you'll find that you'll make better decisions, you'll be more rational, and you might just get at a much deeper truth. All right, that's it for this episode. Thank you so much for listening. If you'd like to support my show, Science in Perspective, you can quickly and easily do it directly by clicking on the support link that you see in any show description. $3, $5, $10 a month. It does a lot to help me make this show feasible. For more dedicated listeners, you can become a member over at scienceinperspective.com. That's science-in-perspective.com, where in addition to having a one-stop shop for all episodes, you can find premium content, a member chat room, and periodic Q&A sessions with yours truly. Premium content has me doing a deeper, dedicated talk on the pattern I covered in each episode, applying it to real-world decision-making. This is for those looking to implement the patterns I discuss in their lives, in their work, and in their creativity for smarter problem-solving, reasoning, and applied knowledge. I believe the patterns I discuss are universal, and the knowledge and use of them can make us live smarter lives. Memberships for Science in Perspective are $9.99 a month. Again, thanks so much for listening. Until next time, take care.